Good morning, everyone. Uh, in my next session, that I concluded in the session one, and it will be continued with the application of ratioed logic, that is a pseudo NMOS logic that we discussed in the session one lecture video. Okay, so let's see that how we can implement our logic, how we can implement this pseudo NMOS transistor logic in this section, that is differential cascade voltage switch logic, that is DCVSL. Okay, so one of the most important application of this kind of design, and here we will see that yes, we will overcome the problem of static power dissipation that occurred in that section, that is in a pseudo NMOS logic. That is parallelly this one is on, and we have to modify the circuit by adding the larger resistance value. But here we will see that we can easily overcome this kind of situation. Okay, so let's see that how it is overcome. I think that is visible to the design, but everything is discussed in the PDF section in the description, so please go through that. But before going to that, please listen carefully that how I am explaining this kind of design. Okay, and everything is written in the description, but before that, please try to understand that what is the logic inside the circuit and how we can implement this kind of logic. Okay, so first one, that is the name is differential cascade voltage logic, voltage switch logic, right? DCVSL, and it's a very important concept in a digital VLSI design. Okay, but what is the significance of this differential, what is the significance of this cascade, and what is the significance of voltage switch logic? But each and every term has some inner meaning that will be definitely reflect in the operating principle of DCVSL. Okay, so this is the general circuit diagram of this differential logic, but at the first point I must say two important points. What is the two important point? For this kind of design, we have used the two logic. One is a differential logic and other one is positive feedback. I think that it's visible to you that why I am saying this positive feedback, because please see that there is a path from output to input, there is a path from output to input. So we can definitely say that the feedback concept is used over there. The feedback concept is used, right? And but what is the significance of this differential logic? Differential logic means it uses both true and complementary input signals, and parallelly it will generate the true and complementary output also. True and complementary output means 1 or 0. Clear? So by using this concept, yes, we will use definitely the logic of this pseudo NMOS logic, because parallelly we will obtain this 1 and 0. Okay, but without any static power dissipation, right? So what is the significance of this the name differential? Because it uses both true and complementary input, and it generates a true and complementary output also. I think it's visible from this diagram. And why this feedback mechanism? We have already seen that feedback path is there, and this feedback mechanism ensures that the load device will be turned off whenever will not needed. And why this load device? What is the significance of that? You all are very used to the term that is RL, right? Because you have already studied in your analog electronics, in your device electronics, that is RL. RL means the load resistance. And why it is used, you all know that. So in order to avoid that kind of load device when it will be not needed, and in order to make simple the circuit, we will use this feedback mechanism, right? We have used this feedback path that is described in this section. We use this feedback path, this kind of feedback path. I think is shown to you. Okay, now let's begin that how it works. Okay, but before going that, I must say that another 2 points, that is that what is this? What is this box? This box is nothing but pull-down network. We all know that pull-down network, and pull-down network means it is designed using NMOS. But parallelly, I must say one point, that these two blocks are mutually exclusive. Why it is so mutually exclusive? Because at a time any one will be on. At a time any one will be on. Parallelly, two will not be conducting. I think it's not required. It's not mentioned that two pull down network will be on at a time. It will not work basically. At a time one of the network will be on. That's why I am saying that two pull down network, this F and F bar, are mutually exclusive nature. And you can also say that these network are dual with each other. For any given input, one of the pull down network will be on and other one will be off. Very simple. Clear? So I am again revising the 3 points. One is your differential logic, one is your feedback mechanism in order to avoid the load device unconditionally, and the another one is using of pull down network, mutually exclusive pull down network that having dual nature of each other. Right? Okay, so let's see that how it will function. Right? Okay, so such assume that you are giving the inputs over here. Okay, and such kind of input that F is on, that means you are giving high input, means 1. So F is on because this is designed with NMOS. So if F is on, then this is the output associated with that. So this output will be, what value we will obtain? The obtained value is 0. Yes, because this NMOS transistor is conducting. So Y is equal to 0. And if Y equal to 0, we have at the beginning I have said that you can apply the normal output, you can apply the normal and complement input, and you can also get the normal and complement output also. So if Y equal to 0, and along to this feedback, this 0 is fed to the gate terminal of P2, means this PMOS transistor. So in PMOS transistor gate terminal, this 0 is coming. So PMOS gate 0, that means this P2 transistor will be on, this P2 MOS will be on, and to pull the opposite output, that means Y bar will be equal to high. So at a time we are getting Y equal to 0 and parallelly Y bar equal to 1, and without any static power dissipation, because we have already discarded this load resistance, this load device, by using this feedback mechanism. So please see that how nicely this concept is applied. This concept is designed using this kind of differential cascade voltage switch logic. Right? And parallelly the opposite, the vice versa, is also possible. How it is possible? Please say that depending on the input, this network is on. So if this network is on, then Y bar will be equal to 0, and this 0 will be fed back to the gate terminal of P1. Again P1 is conducting, so Y equal to 1. Right? So when Y bar rises, it turns on. When please come to my previous point, that is, this one is on, this one is on, but these two is off. How these two is off? Because whenever this network is on, this Y equal to 0, and this 0 is given to the gate terminal of P2, and this Y bar equal to 1, and this 1 is fed back to the gate terminal of P1. So obviously this P1 transistor is off, and this one is also on, because we know that at a time two network will not conducting, will not on. So this one is off, this one is off, this one is on, and this one is on. And parallelly in the vice versa, this will be conducting, but this will be off. Okay, so I think that the logic is clear to you, and you can easily implement this kind of logic with any other design. Okay, so please go through the description that is explained in the below section of this Dcvsl, and try to implement your logic according to your own concept. Okay, so till then, continue watching.